Hi everyone. In this video, I'm going to give you an idea, and I'm going to show you an example of what a sinusoidal steady state is. So my name is Hasathorn Savipan from CPE SIT student. So what is a sinusoidal steady state? A sinusoidal steady state is when there is a sinusoidal voltage source, right, that produces voltage that varies as a sine wave with time. Also, it is when a sinusoidal current source, right, produces a current that varies as a cosine wave of time. So it's different. The wave of time is different, right? So let me show you an example of how to deal with a sinusoidal steady state. So in this picture that I have written by myself, there is a circuit here, right? And we would like to find Vx and Iy in this example. So let's look at V1 at the left, top left. It says that V1 is 10 to the phase shift of 0 degree, right? And I wrote it here as V1 is equal to 10 with the parentheses. And I will show you how did I get that answer. And also at the right, there is V2, which is on the top right here, saying that it's equal to 5 with a phase shift of 90 degree. And there is another form of V2 as well here. It's written here. It says V2 is equal to 5J. So let's look how did I solve it, right? How did I solve that problem? It's V1 equals to the phase shift of, V1 is equal to 10, and the phase shift is 0. And we can write it down as 10 times cosine of 0 plus j sine of 0, which is equal to 10. And for V2, it says that 5 times cosine of 90 degree plus j sine of 90 degree, which is 5j. So that's how I get it, just converting from the polar form. So after we get V1 and V2, we can use the nodal analysis, our basic way, all right, before midterm. So grabbing everything, it says that Vy minus 10 divided by minus J2 plus Vy divided by 10 plus Vy minus Vx divided by 8J equals to 0. Please note that it's better to write J in front so you don't get confused, so you can see the term clearly. What is J and what is just a numeric number, right? It's different. All right, for the second equation here, it's Vx minus Vy divided by J8 plus Vx divided by minus J6 plus Vx minus 5J, all of that divided by 3 equals to 0. So there are two equations in here because there are two variables. You can see that there is Vx and Vy, and we would like to solve for Vx. So let's do some math, right? But I'm just gonna skip that and show you on the next page. Here. So this is the simplified term here. For equation 1, it's Vy multiplied by minus 1 over J2 plus 1 over 10 plus 1 over J8, all of that equal to Vx over 8J minus 5J. For equation 2, it's Vx times 1 over 8J minus 1 over 6J plus 1 over 3. All of that equals to all of that equals to Vy divided by J8 plus J5 divided by 3. So we have simplified all the equations, right? And we're left only with the term Vx and Vy here. All right, let's continue. So for the last part, we can do some math, and we will get and you will get the result hopefully same as me, Vx is equal to 1.21 plus J 0.31. Sorry, it's 0.31 J to be said correctly. All right, after we have got Vx, if you want to convert to the polar form, we can do that as well, but for now I'm just gonna leave it like this. So after we get Vx, we can know Iy very easily by plotting down the equations, right? Filling the equations here. We can see that in order to get Iy in here, we need Vx, and we also need wait, let me see here. Yeah, we also need Vx minus J5, right? Which is you know what it is, right? Okay, Iy is equal to Vx minus J5, which is V2, of course, divided by 3. And to simplify that, we get Iy is equal to 1.21 minus 1.21 minus 4.69J, and all of that divided by 3. So to wrap up, it is not so difficult to deal with a sinusoidal steady state if you know how to convert it, the polar form to a normal form, and then you can just use the nodal analysis that you have studied before in the midterm, and that is done. Thank you very much.